Yeah, we may need to stop. So, and we continue my lecture. So we talk about the vortex identification criteria. Well, one of the problem with this vortex identification criteria, even we all know is very popular, many users, but they have some problem with the threshold, especially like Q. Really, the threshold is users, given. It's empirical. You need to adjust it. But a different threshold give different, pictures, different vortex structures. Sometimes it's very difficult to adjust this threshold. Well, they could be from 0.01, could be 1 million, could be 1 billion when you use Q. So really you don't know what it is. You need to adjust it case by case, even time by time, if we use the time-dependent, work. So we need something not very, related to the threshold. I believe Q is really, because we don't know what the physical meaning is Q. What Q mean? What Q means? We need to understand the physical meaning. So vorticity, we understand vorticity is the Q of the velocity. We know that. Physical, we don't know. Physical, we don't know what the meaning for vorticity. But people usually understand vorticity is vortex, so rotation. But it's not. We already talked that. It is not exactly. Q, lambda 2, lambda Ci, we really don't know what is the physical meaning it is. Well, we were talking, Nutex is clear. It is clear. We were talking, Nutex is rotation. And the direction is the rotation axis. And the magnitude is the, angle speed. Exactly. So that means we really don't need to adjust. But Q, you need to adjust it, I think. And also, this is need to adjust. Well, of course, some people could say, if we adjust the threshold well, the picture is similar. That could be. But also, this could cause some trouble. Like, then what is the vortex, turbulence theory? What is the physics or mechanism of the turbulence generation? So we use graphics, we need visualization. But we may get wrong physics, could be. And let me look at this. This is lambda 2, we use lambda 2. This is lambda 2, when you use lambda 2 a little larger, 0.017. So you got a vortex breakdown. So people get the conclusion, turbulence is created by vortex breakdown. But if you change if you change the threshold smaller, all the vortex link together. So then you get the conclusion, turbulence is not caused by vortex breakdown. Vortex breakdown or not breakdown, this is not by physics, by your threshold. This is not supposed to be. So this could be misleading the people. Could be misleading the people. So be careful with that. So threshold, should be, not empirical, adjustable. We should have a physical meaning. Or best, unique. We will talk later. Unique. Well, this, I think, I didn't put a movie. This is just say use different. I don't think this movie there. I forgot. I may forget it. Here. You could see that. You different threshold, you get different vortex structure. So turbulence generation physics is not decided by physics, by threshold. It doesn't make sense. The turbulence is turbulence. They have certain physics, certain mechanisms. We cannot, they say, they generate by threshold. That doesn't make sense. Well, I talk a little bit about omega method. Omega method really very close to Q method. Well, Q method is B minus A, right? Yeah, but this is not B minus A. The B, that's the F norm, Frobenius norm, F norm. Then there's A norm and B norm, of course, square. So it is relative. But to avoid divided by small number or zero, we add epsilon. So just use this formula. And this is very, very similar to Q method. But what is the advantage? Why is the omega? Well, the omega has apparently advantage. You can try it. You use Q and you use omega. You will find it. What is that? Well, this new epsilon is easy to perform. Since epsilon in the can be auto-adjusted by fixed number. Yeah, we just give some empirical formula by B minus A maximum, and we put 0.01, something like that. The epsilon is not very difficult to adjust it. It is, depends on I think there's a rounding error. And omega also, we don't need adjust it much. Well, use Q omega, they about similar or same, similar. But what is the advantage of omega? Omega, you don't need to change. You just put 0.52, then that's all. You don't need to make many, times adjustment. When you do the engineering problem, you have to adjust the Q to get appropriate graphics. But when you use omega, you don't need to adjust it. That's the advantage. Yeah. Well, you will find it. Yeah, sorry. What's wrong? Oh, almost down. Yeah. Omega. Yeah, we put 0.52. Well, you can put 0.6 anyway. They change a little, not much. Well, it's normalized. So 0 to 1. Omega, the good things, they can capture the, more turbulent vortex structure. Yeah, and also the strong vortex and weak vortex simultaneously. Yeah. So omega is a number. It's a number. Use this number, use the omega method, you can capture more vortex structure. Especially, you have, capability to capture both strong and weak vortex. The reason it is, clear why saying that. For example, one vortex rotated 1,000 per second, 1,000 circles. The other one, it is 10. Then if you put the threshold 100, the 10 disappeared. But use omega method, they may be able to capture the 10. Because omega really is, really is vorticity over the vorticity plus shear. Really is that. This is relative. This is will make it easy. That's why I checked website about citations. More people cite the Omega method than the new text. They appeared almost the same time. The Omega, because the reason why Omega is easier. It's easy to do. Well, it's nothing worse than Q. Nothing worse than Q. But easier than Q. Because you don't need to adjust it. Yeah. So that's the advantage. As I said, what the problem with this vertex identification method, there is a scalar. They need a threshold. But a threshold is man-made and empirical. They are all contaminated by shear or stretching. They are not a pure rotation. What is it is not, Q is not, all others are not. And the physical meaning is not clear, really not clear. Like we know the temperature was a physical meaning. The temperature, we know if it is 70, or you say it's warmer. If it's 50, cooler. So the physical meaning clear with the temperature. So what is the physical meaning with Q? Lambda 2, lambda CI? Really we don't know. What the physical, really we don't know. What's the physical definition? Also, they are very strongly threshold dependent. So that's not unique vortex structure. This is more serious. If not unique, that means we don't have vortex structure. A different threshold gives different vortex structure. Which one is real vortex structure? We don't have. This is more serious, especially for turbulent research. The turbulent research need exactly vortex structure. Exactly vortex structure should be unique. Cannot be many, hundreds, thousands, 10,000s. You cannot be that. So that's the problem. Really seriously, turbulent researcher need to realize that. So far, we don't have anything to give a unique vortex structure. You look at the book for turbulence. You look at the book. They give different pictures. Something like a piper, something like a fish, something like an insect. So what is turbulence structure? No, that depends on what kind of method you use, what kind of threshold you use. That's not a serious turbulent research. On the other hand, we say we don't have serious turbulent research. We don't. We don't have vortex structure. The more serious. I think now here a lot of people may try to, spend a knife or spend to find what's the mystery of the turbulence. Well, first we need a unique vortex structure. We need a vortex definition and a vortex, unique structure. The reasons why. Look at all the turbulence. They're all filled with vortices. They say that we get turbulent flow. We didn't find the vortex. You cannot find the truth. You cannot find it. When you find any turbulent flow, there's a field of the vortices. We need definition for vortex. We need unique vortex structure. That's the necessary condition, if not a sufficient condition. It's a necessary condition. Okay, thank you. That's the first. Then I talk the second. So I'm in it. Thank you. And let me get after this and go to the second lecture. Huh? Okay, now we talk about third generation. So we call it latex. Latex really, that's the, well, I just met some students. They say, so they understand my idea. They say, well, what means latex? Latex means you have vorticity, right? But the vorticity has shear and rotation. If you throw away the shear, then you get a latex. That's clear. So what is latex? You have vorticity, right? Throw away the shear, you get a latex. That's the major idea. That's the major idea. That's true. That means that these students, so students understand what I'm saying. So first, I need to talk a little bit of the mathematics foundation, eigenvalue and eigenvector. Well, suppose everybody understanding, well, maybe the math students have no problem with that. But for the engineering students, they may have some problem with this, eigenvalue and eigenvector. Then I talk about my confusing, and where we talk coordinate system rotation, and principal coordinate, and principal matrix. And then we give the Newtek definition. For local rotation, well, for global rotation, I think this definition is not mathematical. It is not. So that's what we explain. As I said, we need to understand vector tensor. This is the physics. Vector is vector. Like velocity is a vector. But the mathematics, they have metrics. Well, could it be square matrix? Could it be a row? Could it be a column? That's the mathematics. Never confused by the physics and the mathematics. Be careful with that. Because, the future, this is, the vector is at least Gardinian invariant. That's in the Earth. Invariant. They cannot change. Or better is objective. We are not related to any coordinates. But the mathematics is a matrix. They directly rely on the coordinates. So one vector, you have 1,000 matrices. One tensor, you have 1,000. So don't mix the physics and the mathematics. This is unique, this is infinity. So for the operation, where we know that the physics, we have dot product, you have cross product, you have dyadic, But for math, they don't have that. They only have plus, subtraction, addition, subtraction, and multiplication. Inverse, transpose. That's the math. This is physics. Don't mix them. But how we talk about physics? Physics is, we talk speaking, talking. Mathematics talk about formula. They only rely on the formula. So this is different. So physics to the math, be careful with that. Look like this is a vector. This vector in these coordinates is 110. This vector. But when you rotate the x, y coordinates, it's square 2, 0, 0. Vector is 1. We never change that. Different coordinates will have different metrics. Be careful with that. Matrix could be infinity, but vector only 1. Tensor only 1. Unique. Be careful with that. So we already know that, like U dot product, that's the physics. When we become mass, well, you need a transpose. Left part need a transpose. I hope we don't confused by that. Like a gradient of V, it's not a gradient of its transpose. If not symmetric, you cannot do that. But I think we find that the book they don't want to make difference. They just say sometimes it's this matrix, and sometimes use the transpose. It doesn't make people confusing. That's one of the reasons why so many years people didn't find a new text. This new text is very simple. You just make a division, decomposition, 2 parts. Throw away the share. Well, how to throw the share? That's because our, misunderstanding between math and physics. We meet the difficulty to find the new text. So, as I said, the vector product, and this is tensor product. That's my opinion. Okay. Well, this is not in the book. So this is a dot. This is physics. We don't have a dot in the mathematics. Throw away. You need a transpose. When you get the same results. This is dyadic product. People also throw away. they throw away dot product. Dyadic, throw away. Then sometimes add, sometimes throw away. You cannot do that. You cannot do this. This is physics. When you do that, you need to change. Through the dot, you need a transpose. Through the dyadic, you need a transpose. Right side. Right matrix. So that's what I say. Be careful that. That's my opinion. But it's not in the book. Okay? So that's the Hamilton operator we use very much. We say, well, this is del, the Hamilton operator, dot product. Well, really mathematics, we transfer to mathematics, we need transpose del. Transpose del. This is the del, this is transpose del. Then we get results. Then we talk about dyadic. You throw away this. Some people plug it in and throw away randomly. No. You need a transpose of V. Then you get the results. So we cannot, randomly add or throw away this dot product, the dyadic product. People usually do that. You do that. They throw away, they add something. You cannot. Okay, I just give examples. Then this is a matrix. Then we need to find the, eigen value. How to find eigenvalue? I think we just we call it characteristic. This is really polynomial. Then we get the equations. And then we solve this equation, we get the roots. That's eigenvalues. I suppose you have knowledge about eigenvalue and eigenvector. Suppose you have. Well, that's important. That's very, very important, eigenvalue and eigenvector. So you need to solve this determinant equations. And this is polynomials. Then we get 3 eigenvalues. Well, that's all real, different from our rotation. Well, also, we talk about the eigenvector. Well, eigenvector, I think it is a little confusing. Yeah, a little confusing what? Because this A minus lambda I, it is singular. The singular determinant zero. So you really don't have, you either have no solution or infinite solution. In our case, it's infinite solution because right-hand side is also zero. So eigenvalue is unique. Eigenvector is not unique. Be careful with that. You have hundreds eigenvector, but this is a subspace. For example, for this one, we solve this equation, we can find x, y, z, then we can find the eigenvector to find it, right? We find the eigenvector, you see that? We have minus what we have it here. Yeah, the equation is like here. And this is not the unique solution. We don't have a unique solution. So we have, minus 1, 1, 0. This is we call it subspace. Y and Z is the random. You can pick anything. So we solve this. We get this 2 by 2 right now. We solve 3 by 3, 2 by 2, I think. So we find well, if lambda 1 is 3 by 3, lambda 1, we get 2 eigenvectors. One is negative 1, the other is this one. Well, this is not unique. You get a 2, negative 2, 2 is also eigenvector. But in general, you can write this. You can write this formula. So really, we say the subspace just spanned by these two vectors. The 2 vectors. If lambda equal 2, we can get another eigenvector. So we get 3 eigenvalue, we get 3 eigenvector. Yeah, that's according to math. Be careful with that. This is not unique, as I said. It's not unique. Any, times anything, even positive or negative, in times negative 1, it's still eigenvector. Time 100, still eigenvector. This is just a subset spanned by these 3, vectors. So be careful that. This is why it become important. The reason is, we may get the wrong eigenvector because the eigenvector is not unique. Eigenvalue is unique, especially when we do the transpose. The transpose, the matrix, it doesn't change the eigenvalue, but it did change the eigenvector. That's the problem. With why we take so long time to find the mutex. Why it takes so long time? Yeah, because people transpose the velocity gradient tensor, they transpose. Then they cannot find the eigenvector. They cannot find the rotation axis. That's the problem, one of the problems. I think why it takes so long time? Or there's another example. So there's another example. The other example just to say one real eigen and one real eigenvector, real eigenvalue, and 2 conjugate, complex eigenvalue according to their rule. I think this is where we can find it, and then we can get eigenvalue 1, this is conjugate, 1 plus 2i. This is another case where this nature, velocity gradient tensor is a physics. We cannot change it. But mathematically, they say you have two choices. One, you have 3 eigenvalues. The other say 1 eigenvalue and 2 complex. Well, the complex already appear as a pair. So in the nature, we only have 2. We don't have 3. 3 maybe 0, all 0. Okay, either 1, 3 real eigenvalue, and 1 real, 2 complex. Physically, we say it's law rotation and rotation. If we have 1 eigenvalue real and 2 complex. But this just show the other way. The other way just give you, a real eigenvector. This is one, the other one. Well, it depends on the, that's what I say, depends on the coordinates. Okay? Then we get 2 complex eigenvalue. Then corresponding, you get 2 complex eigenvectors. I think lambda CI, they use these 2 complex eigenvector be 2 real vector. That's the method they use. So they get 1 eigenvalue real and 2 complex. For the vector, they have 3. 1 real, the other from complex. Complex 2 parts, real part and imaginary part. They put the real part as 1 vector. They put the imaginary part as another vector. But in this system, they are not orthogonal. Be careful with that, not orthogonal. So that means in general, you cannot get an accurate answer. Maybe, approximation, not a regular. But they call this swirling strength. But it is not a swirling strength. Not a swirling strength, yeah. Approximately, you can say that. So, first, as I said, we need all mass. This is all mass. Yeah, all of mass. dv is a vector. dv is a velocity increment. dv is exactly mathematical definition, vector. Then this vector we can write what's du. The du we can use mathematical for du. The partial u, partial in the 3D. Partial u, partial y, dy, partial u. The exact definition. Okay, the exact definition. Well, of course, here we don't consider high order, only first order. Then we get partial u, partial u, partial u on the first row. The partial u, partial u, partial. This is all exact mass. There's nothing related to the physics. That's mass. You see? But when we go to the physics, we talk the tensor. Well, tensor is not necessary to be matrix. When we put a tensor, we put a dot product. The dot product is not for mass. Dot product is for the physics. That's the tensor product vector, the projection. That's the physical meaning. When we put a dot here, we need a transpose. U here. V, U is row. U become a column. then we can get, gradient V dot dl. That's a trick that we put. Well, I try to. Well, you can check your computer. The book and the wiki, they say a different story. Wiki or Google, a different story. What difference? The difference from here. U. I think on the first row, that's in the American textbook. That's in the American textbook. They call this gradient of the V. But then they randomly put the dot here. If randomly put here, you can never get a mutex. They get an eigenvector, but not mutex. Not rotation. Not a rotation axis. They randomly put a dot and take away, plug in, take away, and not. Well, that's what I say. When you plug it in, you need to make a transpose del V. Otherwise, it's not correct, because even you didn't change your eigenvalue, you change your eigenvector. So I guess that's one of the reasons why it takes so long time for people to find the mutex. Why? They cannot. You can use this. Well, you can find this is from American textbook, even math book. Math book, yeah, you can. But if you want to find the eigenvector, it is not mutex. You can find it's not mutex. But if we use this, if we find the eigenvector, it is mutex. That's the problem. That's why it takes so long time. Well, that's the problem caused by math and physics. They mix them. They mix math and physics. They randomly add, dyadic dot product, cross product, randomly. They like put in, they don't like take away. Including me. Including me, yes. First one?
Why do you put it in the column instead of a row?
You mean here?
No, the first one.
First one?
Yeah.
Well, we use the vector, use the row matrix for the vector. Well, that's you can use use a column, not a row. Use a column, but that's a mathematical book mostly use. But you can use the row as well. But then you can use transpose. Yeah. You can use. Yeah, we usually use the row or column as a vector. We don't use this. We don't use this. We don't use like V equal to UVW. We don't use that. The math usually use the column. We only agree column for, well, some books they say column and row are same. Yeah, some not the same. Well, this is math. Math is just people agreement. So we think it is, when we talk about a vector, we use a column. Yeah, that's just the general agreement. Yeah, but you say starting beginning we use a row as a vector. Well, okay, but everything is different, and then you have the problem. You have the eigenvector problem. The eigenvector is not a right eigenvector; it's a left eigenvector. So that causes the other problem. We just use general math book. Just use column as a vector. You can use row as vector, but then you totally different. Then your eigenvector is on the left, not right. That could be, yeah, that's the problem. Well, well, does it say? Well, first, we don't have any uniform, for the velocity gradient. Well, that's hard to talk. The book, the Google, the wiki, they all give different. This is very important. Well, you can do that. You can test it. There's two different, metrics. They have same eigen value, but different eigenvector. But I believe most of the American textbooks use this. This is incorrect. This is not correct. So you make the mistake from beginning of the textbook. You cannot do that. Yeah. But the condition is we agree. This right vector is the eigenvector. Column matrix is vector. We agree. Well, math is agree. You define it. That's a main logical conclusion. That's a main mind. Yeah. So we have no problem with this. If we use this, we can get an eigenvector. That's a new text. Then if we use this, we can use the diode, then we can have no problem. But apparently in wiki and most Western fluid dynamics, the gradient tensor is really this. It's gradient tensor transpose. They use transpose instead of, well, there's mathematics, you cannot do that. You do that, you change your eigenvector. Even you didn't change your eigenvalue, you change your eigenvector. Well, some people maybe argue. We accept both, column and the row are vector. We accept both right eigenvector and left eigenvector. Well, you say that. Well, that's cause more confusing, I think. To cause more confusing. You want to say they try to answer my question, even cause more confusing. Well, which one it is? So that's the problem. That's what I say. Be careful with that. Be careful with wiki. Be careful with Google. Yeah, they cannot. Well, that's the people wrote. Yeah. They wrote based on their understanding. They made a mistake. They don't understand the mistake. That's it. Yeah. We want to get the consistent, not inconsistent. So my confusing, first, when I get old, as I said, gosh, I studied fluid dynamics the whole life. I talk to the students. I studied, Navier-Stokes equations, try to find how to get it at least 100 times each term. 100 times. When I get older and older, gosh, I say, well, my study is a misunderstanding. Suddenly I find it. I cheat myself. Suddenly I find it. With many, many contradictions. Let me see. Vorticity line, vorticity phenomena, vorticity tube, vortex. That's one misunderstanding. Yeah, what I said, when I ask a student, well, if the vortex is a concentration of vorticity, that means in the vortex center, your vorticity is very large. It is true or not? The student answer is opposite. Vortex is not the concentration of vorticity. The vorticity is large, not vortex. Vorticity is small, strong vortex. Well, the answer is just the opposite. Actually, I think I'm cheated by these textbooks. I'm cheated. This is all books say. What text? What is it concentration? What is it is energy? They all say that, including myself. That's what I said. I'm not rich. I'm a poor, poor family. So my, not developed that fast. When I get 70 years old, I find it. I cheat myself by these books. Unfortunately, that's not true. It's wrong. What is it? It's a clinical mathematical definition, but it's the curve of the velocity. That's clearly. That's what is it. Why we say that what is it is a fluid rotation? Who said that? Who gave the proof? Do you have experiment, or you have the, or you have the, numerical simulation? Tell this. Who tell this? Nobody. I think there's one given by American, Academy of Science, American Academy of Science, given by, I think, very famous, Shapiro. You check the YouTube, given by the Shapiro. They show. You don't think that. You look at this. Let me have what here? A channel of matter here. We put we put a fan here, then the fan rotated. So they say, what is it is vortex? For sure. They published by the American Academy of Science in the 60s. And it's still in tube. And some professor told me, this is the truth. If you want to change one word, that's waste time. Change one word of Shapiro. It's waste time. Well, this is true a lot. You put the fan here, it's rotated. How you put the injection by ink? Law rotation, the laminar flow. I think my student did an experiment. I can find they show you this. I think this is somewhere maybe. Yeah. Well, so you understand what I'm saying? If you put a fan here, is rotated. There's no question. But the fluid is a fan. The fluid is a fan? Or, yeah, fluid is fluid. Fluid is not rotated at all. Fluid is a laminar flow. No rotation at all, no vortex at all. This is published by American Academy of Science. Most classical, most traditional, but it is misleading. Well, if we don't agree, do you agree? This is Shapiro's experiment. He said, we have vortex. What is it? Near the wall, what is it large? Vortex is large. You don't believe? I put a fan there. You see? It rotated. Do you believe this story? That means our channel flow, our flat plate flow, all made by fan. That's impossible. We cannot make fluids by fan. We have to make fluids by fluids. There is no rotation at all. I'm not sure. I always, challenging this kind of the classical theory. Always challenge that. Until one is get 70 old. Like I say, I study fluid dynamics whole life, all misunderstandings. But you can find it from YouTube. You just Shapiro's experiment. You see what they tell me. They're published by American Academy of Science. It's very classical. This is very classical mistakes, very classical misunderstandings. Same thing, they say, circulation is large, the vortex is strong. Who tell you? Who tell you that? You have circulation is very strong, so no vortex, zero. They mix the two concepts. Fluid is fluid. Fluid is not solid. They put a fan there, the fan is solid. Fan is not, the airfoil is not the fluids. Airfoil made by fluids? It cannot happen. I also get confused. Well, this is mathematical. My confusing, the vorticity, the dot product is zero. Yeah. The flux is constant, which means vortex can never break down. This is clear, tell you. The textbook say vorticity is vortex. Vorticity cannot break down. That's by the mathematics. You cannot. That's exactly. But in the same book, they tell you how to turbulence generate. Turbulence generated by vortex breakdown. What that mean? Vortex is vorticity. Vorticity cannot break down forever. Vortex turbulence is created by vortex. What that mean? What that mean? Your book against your book. The book against the book is himself. That's what I say. Net part against the only part. Well, we say vortex is natural. It's a natural phenomenon. But vorticity is the exact mathematical definition. Why they should be equal to each other? Why? Do you have any reason? Any mathematical proof? Do you have any? No, I don't think we have any. Well, if anyone you have different opinion, you just raise hand and say, I don't agree. I don't agree. Yeah, you say. Well, so that's I got confused. The turbulence is headache. Everybody says the turbulence headache. We cannot understand. We cannot understand for the past. We cannot understand for now. We cannot understand forever. That's the most people conclusion. Because this is you against yourself. You give another definition against yourself. Well, that's I say, I already showed this already. So you know that. Well, I can understand the author, the book author, may never did a DNS, may never draw the picture, may never draw the vortex, may never draw the vorticity vector. That's understandable. They copy each other from here to there. We're all the same. But if you do by yourself, you check that. You check that. You say, no, forget it. You can use Q. You can use lambda 2. You can do that. Then you put the vorticity now to see they parallel or not parallel. This can prove that. As I said, one counterexample is good enough. It's good enough. They're finished. When that's finished, then let's forget this theory. But if you draw the new text isosurface, then you draw the new text vector, they are parallel. As I said, one counterexample, I agree, we need to give up the new text theory. So you understand what I'm saying? Yeah? I don't think this is correct. This is correct. Vortex line, the vorticity line. It is the same thing. Already, I showed that already. But this is not only the two books. Well, this is not fair. all of the books, all of the fluid dynamics books, in all of the countries around the world. No exception. I don't think there's any exception. Yeah, no matter which university it is. They all use this concept. I put this, I copied this from website. That's the MIT. That's the MIT online lecture. Online lecture. What did they say? You can read that. They just repeatedly the Helmholtz 3 laws. Unfortunately, none of these laws correct. None of this. Well, we cannot blame, because they many years ago they're very smart. They're very, but they don't have computer. They don't have instrument. They don't know how to measure, the vortex, how to measure the vorticity. I don't know that. They just by the imagery, imagine. They say, they give this. Well, we still use. We see it online to teach the students. What did they say? That's I said. I said, well, don't talk about it. Number one, wrong. Number two, wrong. Number three, wrong. This is still online lecture to teach every student. Well, don't give me the face. If I'm wrong, stand up. That's again. If I'm wrong. Okay? So you know that, yeah. Just the opposite, unfortunately. Apparently, yeah. That's what I said. Even the second war, and on the war is zero. Zero, you against the first theory. So I don't think this is a good answer. Yeah, that's what I talk already. No question. They say, vortex is vorticity. No question. Vortex is measured by vorticity. Well, this is encyclopedia. Yeah, encyclopedia. That's a book. The past. Well, I say that. That's I don't want to. Repeat again. But I think when we give the new text, this is revolutionary and groundbreaking. This will open a new door, open. For what? For turbulence research, for vortex science research. I'm just joking to say, well, I talk to some, at a mass fair people. Well, I say, well, you give the, forecasting, give what? Give temperature, velocity, give, and vorticity. And vorticity. Vorticity is important, amount, or we say quantity. Very important. We must give this forecasting station. My question, why? Why you don't give new text? Why when you do the weather broadcasting, you don't give new text. If new text is exactly what text there. Why give fake the new text? What text? I don't understand. That's one of the things I don't understand. I don't understand. Well, this is, I think, repeated. Yeah. Well, this is also I repeated. Yeah, I said, really, Rubin said 1989. He found this correlation is very weak. And one, we say, well, 2016, that's use lambda 2 as well. They found just opposite. The vortex inside the vortex, vorticity is small. Outside the vortex, vorticity is large. It's just opposite. This is the opposite. Yeah, we showed this already, I think. Yeah, we don't need to repeat it again. So, the vortex, the plane, the section is the measurement of vorticity. You can see that. There's a vorticity there, all this area. This is small. This is vortex. This is a vortex. Is small. The vortex is small. And outside, vorticity is very large. It's just the opposite. So from this, you can get a conclusion. Vortex is vorticity. So vortex is strong, vorticity is small. Vortex is zero, vorticity is large. We can use vorticity? It makes no sense to me. It's just opposite. This I also show you. Oh, this is a vortex, then this is a vorticity. Well, they're orthogonal. They're not parallel. They're orthogonal. They're orthogonal, unfortunately. Well, as I said, you come back. So what is a vortex? Well, we only talk about a point vortex. Point vortex. Yeah. But one point. The point vortex is what? You need to have one axis. You need a rotation. That's two things. Any, absent of any one, or no axis, or no rotation, it's not vortex. Okay? That's the okay. So we need to give definition. I think must be local at each point. Don't forget it. Temperature, pressure, velocity, vorticity, all given at one point. I didn't see they give definition for hurricane or for tornado, how to give. This is the global. Unique, we must be unique. What means unique? Unique, that means we only have one method. You cannot say, Q give one, delta give one, lambda 2 give one, lambda CI give one. This is 4. Even we don't consider isosurface problem, you give 4. Unique, that's unique, we must. Vector, we have direction and magnitude. Like Q, lambda 2, they're scalar. They automatically lost the candidates. We need gardening invariant. That means in inertial system, independent of coordinate system. We cannot say we use different coordinates, we get a different definition. This shouldn't be. Independent of coordinates, that's more important. Well, then we talk gardening invariant, that's meaning in the Earth. Even after the Earth, we need to give, we call it objective. That's not related to any, because the vortex strength cannot be changed by your coordinates. Otherwise, it is not a definition. The definition is definition. 3 is 3, always 3. No matter in your coordinates, in Earth coordinates, in space coordinates, they never change. That's the definition. systematic, as I said. We give the Newton definition. They have scalar, vector, and matrix. Systematically, not only one. Then we're not related to any dynamics, as I said. That's another requirement. Then we have vortex definition in thermodynamics, in two-phase flow, in three-phase flow, in combustion, in the hypersonic, in the well, then we have many definitions for vortex. That's what we don't want to. We don't need to. We need only one, unique. Make sense? You agree? Yeah, you agree? I agree. We give a definition, just like temperature or pressure. Well, they fix. They 3 is 3. You cannot say, I change my coordinates, they become 5. That's not definition for pressure. Right? Yes. Yeah. Yeah, inertia. Yeah, inertia system. No, not only inertia. Yes, yeah, yes. Should be, yeah. Also, if a non-inertial system, it also shouldn't be changed. So we will talk later, yeah. That's inertial system is the basic requirement, very basic requirement, yeah. Velocity is not independent to the coordinates. Apparently is not, right? Yeah. When you're standing on the train station, the train moving, you didn't move. You think you were moving, because of the relative velocity. This is not a coordinate, not the, they call it Gardner invariant. We must satisfy this condition. Be careful in the fluid dynamics. Be careful with that. That's what I give the requirement. You give definition, you check if you meet this condition or not. If not meet, you lost your candidate's qualification. You shouldn't put here for the definition. Because of this conference, you talk about vortex definition. If we don't satisfy any of them, you lost candidates' qualification. Yes?
Can we say this vortex is purely kinematic?
It's in general, yes. Yeah.
Kinematic.
To the kinematics definition, really. It's not related to dynamics. Yeah. Because the only thing you give to me, velocity field. That's only give me. I don't know where is the velocity, field, but you give me. Data you give me. You understand that? You measured, or you measure. Also, this measurement could be different. Because, as I said, you measure the velocity, it's different. You want to measure, when you take a train, it's different. When you're standing, it's different. When you give the measurement, as I said, give to me, then I give the new text from your velocity equation. That shouldn't be changed with any coordinates. Inertial system is a minimum requirement. Dynamics, not dynamic, I don't know how to get it. So that's not related to compressible flow, high-speed flow, supersonic, hypersonic flow. It doesn't relate to us. Different from lambda 2. Lambda 2 incompressible flow, inviscid flow. Well, this is dynamics. No, we give the definitions, not dynamics. The kinematics. You're correct. The kinematics. So axis. Fluid rotation around the axis with stress, not related to coordinates, that's Gardner invariant, not related to dynamics. Since local, as I said, is we talk about vector, all this lambda Ci, lambda 2, Q, delta are excluded. But then the candidate is what is it? What is it? I talked a long time. It is not. It's not a candidate. We don't have any candidates. Only one candidate left. If you say you have other candidates, tell me. We have no candidates. Only one left. That's a new text. That's a new text. So the new text is a vector. The all is direction. All we say is a rotation axis. This capital R, it is magnitude. Where does it define? I think one, they give explicit formula. It's like this. But this is really vorticity. This is vorticity. And this is the lambda Ci. That's the imaginary number. Well, really, this part, you could think is the shear part. Really, it is vorticity minus the shear part. Really is that. Then become pure rotation. We call this new text. Well, in little story, originally is called a root-X. Root-X, if you find our old paper, we call it root-X. In our POF. Well, then we published a couple number of papers, and I received an email. They say, the root-X is given by me in the conference Shanghai. Yeah. Dr. Xu knows the story. Yeah. They say, you didn't mention that. So you need to write the apologize letter, official letter, and publish it in fluid, physics of fluids. Well, I said, well, can we just put your name in our, following papers? We just put his name, and in the following 3 papers at least, I think, was a doctor, and gave this root-X name. And he said, no. This is not the solution. You cannot. You must publish the official letter to apologize in the physical fluids. Well, Dr. Xu joined the discussion. We discussed half a year. Then we decided, no, we change the name. Change the name to what? New text. Nobody challenged that. That's not a very happy name, you understand, to many people. So you're not tired, you're not equal to be proved. We talk about almost half a year, I think. Then I've been to several Chinese Academy members get involved, I think. The guy from the JHD, yeah, he's an academic, not the Dr. Zhu, is another one, the chairman of the editorial. He is the academy members, I think. Yeah. Get involved. we stop the argument anymore because this is a group discussion day by day. Well, we change name, okay? We call new text. Do you have claim? We steal your intelligence? Because it's given by me. So that's a very simple solution. That's I explain that. Some people may say, gosh, you sell yourself. We have some story. This is a true story. This is not joking. The true story, yeah. We discussed more than half a year about this name. Sorry about that. It's like joking, but it is true. Okay, so what is the local axis? What is that? Does I give this the definition? You see that? dV is we call the definition 1. A local rotation axis is defined what? A vector. They only have stretching along its length. But you say this is rotation. That means you only can change the speed in this direction. You cannot have rotation. And thus I give this definition. We call it definition 1. The starting point. Do you agree or not agree? The rotation axis, you cannot rotate it. People, the other rotate around you, you cannot rotate it. You must only have stretching or compression. That's what we call the definition 1. So how to get the definition 1? You see, dV, as I said, is gradient V dot R equal to AR. If R is eigenvector, alpha is eigenvalue. Well, this math, the mathematics, where the math exactly match the physics. So we get a new text. How to get it? This is the method. Okay, well, these are not of, stories. But I say, for me, I just give this concept. The rotation axis only can be stretching. That's what? Eigenvector. The mathematical eigenvector match time a vector and this still original vector. That means only stretching. You didn't change the direction. Matrix time vector didn't change the direction. It's still the vector. This is eigenvector. Eigenvector is what? It's vortex. It's vortex. It's rotation. The local rotation. This is the idea, original idea from this new text. Well, this one we can talk later. We can also get, easily from metrics. Oh? We pass the time. When we started, we need, well, it doesn't matter. We have time. I maybe need to speed up. It's 12, says? 12 is nonchalant.